Now, we're going to look at the second part of this chapter, another important aspect of visible light, and that is the polarization. Polarization. Light is a transverse wave. All electromagnetic waves are transverse, which means the direction of propagation and the direction of oscillation are perpendicular to each other. Okay? Perpendicular to each other. So, what's so special about transverse wave? All transverse waves can be subject to polarization. What does that mean? What's polarization? Polarization means the direction of oscillation in a plane that is perpendicular to the propagation direction. The direction of oscillation within this plane has a specific orientation. Okay? Has a specific orientation. That's called polarization. An unpolarized light, an unpolarized beam of light, can oscillate in all possible directions. That's within the plane that's perpendicular to the propagation direction. But a polarized beam can only oscillate in a certain direction within this plane that is perpendicular to the direction of propagation. Okay, polarization is a feature of transverse wave. We can see that clearly by this diagram. Now imagine, actually, let me look at it. Let's look at a mechanical analogy first. Suppose I have a restrictor like this. Okay, so basically what this is, just just a long narrow opening. Now I have a rope. Okay, I have a rope like this, and I send a wave through the rope. Okay, in this case, the long and narrow opening is along this direction. Okay, is along the vertical direction. Now, if I start an oscillation in the vertical direction, this rope can easily oscillate even within the restrictor, so it can pass through. The wave can pass through. On the other hand, what happens if I try to oscillate the wave like that, horizontally? Well, this wave will not be able to go through this this restriction, right? Because it can only has space up and down in the vertical direction, so that wave cannot go through anymore. So that will be blocked. So any wave passing through this restrictor will only be oscillating along the vertical direction, not horizontal direction. So it becomes polarized. Okay, this will not be the case if the wave is a longitudinal wave. What's a longitudinal wave? It's like a spring, right? Say I have a spring like this, and then I send an oscillation along the direction of propagation, so along the spring, so the spring will oscillate back and forth while the wave also travels in the same direction. Now this time, if you have a restrictor like this, it doesn't matter, no matter what you do, it always goes through. Okay, because you don't have to oscillate up and down like this or like that, which is not possible. Okay, so you have to look at a transverse wave in order to study polarization. No such thing as polarization for longitudinal wave. Now light happens to be a transverse wave, so we have to look at polarization. No such a thing for sound. Okay, sound, as you know, is a longitudinal wave, so we never talk about polarization of sound. Okay, now going back to the case of light. Here we have a red vector indicating one possible direction of oscillation and a green vector indicating another possible direction. Okay, any oscillation direction within the plane that's perpendicular to the x-axis must be the combination of these two directions. Okay, so this is the x direction where the wave travels, and the red may represent the y direction, and the green may represent the z direction, and so on. Now, you can only oscillate in a yz plane. But suppose I let light go through a polarizer. This polarizer is such that after going through this polarizer, only this green vector is preserved. In other words, no oscillation is possible along the red direction because of the way the polarizer is designed. Then after going through the first polarizer, the red component has completely been removed. Okay, the oscillation has only one direction, and that is the green direction. Okay, the green direction. Then we say light is now polarized because it's only got one specific direction of oscillation. Okay, and then what happens if you put a second polarizer? This polarizer can only allow oscillation in the red direction, but there is only a green component left in the wave, right? There is no red component left. So after going through the second polarizer, what happens? No light can go through anymore. These are two polarizers that cross each other at 90 degrees. Okay, no light can go through both of them. After going through both of them, both components, red and green components, are removed. You got nothing left. Okay, so you can use a polarizer to allow certain type of oscillation to go through while blocking other types of oscillation. Now, in general, how much intensity do we have left after light goes through a polarizer? Well, let's say, for simplicity, let's say the original oscillation is already polarized in a certain direction. We call this vector E naught. Okay, so the original electric field exists in certain direction. And then we go through a polarizer. This is called the axis of the polarizer, or polarizing axis. What that is that light, after going through this polarizer, can only oscillate in that direction. Okay, now the original electric field has two components. One is along the polarization direction, the other is perpendicular to the polarization direction. And the angle between the original E field and the polarization axis is theta. So what happened after polarization? After going through the polarizer? Well, this component can go through, okay, because it's along the polarization direction, and that component has been removed. It cannot go through that. And therefore, after going through the polarization, the electric field has a magnitude E, which is related to E naught. You can easily see from this diagram, okay, that E equals to what? E naught times what? Cosine theta, right? And we cannot see the electric field directly. We can observe the intensity. Intensity is proportional to the electric field squared. So we square both sides. What do we get? We get I equals I naught cosine squared theta. Okay, this tells us after going when a polarized beam of light goes through a polarizer, so it's already polarized in one direction, okay, in this direction. Then we let it go through a polarizer. That polarizer has its axis and an angle theta away from the original polarization direction. Then after going through the polarizer, what is the intensity left? The intensity after emerging from polarizer is the original intensity times a factor of cosine theta squared. In particular, when theta is equal to 0, okay, that means the polarizer is oriented in the same direction as the original E field direction, then nothing gets blocked, everything goes through, I equals I naught. On the other hand, if the polarizer is aimed at 90 degrees from the original direction of polarization, then nothing goes through. Okay, nothing goes, just like, you know, this case and that case, right? You let this beam try to go through that, nothing goes through. So, and the factor in general is cosine theta squared. Okay, and what if the original beam is unpolarized? Well, the original beam is unpolarized. That means the original angle, the original E naught can have any direction, right, within the xy plane. In other words, this angle theta can have any value between 0 and 360 degrees. Agreed? Okay. Now, if that's the case, what is the intensity after you polarize it? So you have an unpolarized beam. Okay. The actual direction of E can rotate within the YZ plane. You go through a polarizer. What kind of intensity do we have left? Well, what's your intuition? The intuition is, look, there are only two possible directions, X and Y. Any real direction is always the combination of X direction component and Y direction component, right? Now, if you block one of them, say you block the X direction, you only have Y direction left, how much light will go through? Well, I would say 50%, right? Because the original beam is unpolarized, it's got 50% chance of pointing X direction, 50% chance in Y direction. So you block half of it, the other half is left. So you would expect half of the intensity left. Is that right? Okay, well, let's see. We can see some simple math. If E naught is unpolarized, such as light from the sun is unpolarized, this E naught can point in any direction. Theta can change evenly between 0 and 360 degrees. Then I would have to use this. I equals I naught times the average value of cosine theta, because theta changes. Okay, it's not a constant anymore. What is the average value of cosine theta squared? Well, you see, sine theta squared plus cosine theta squared for whatever angle theta is always equal to 1, right? I don't care what that angle is. And if I average it over one whole cycle and average it over one cycle, it's still equal to 1. But averaging over one whole cycle, if you average between 0 and 360 degrees, you know the average value of sine squared and cosine squared are actually equal to each other, right? So each of them has an average value of what? 1/2. This is 1/2, this is 1/2. So therefore, you have 1/2 I naught. Indeed, just like our intuition says, after going through a polarizer, an unpolarized beam will only have half the intensity left. The other half is blocked. Okay? That formula is called Malus's law. Malus's law. Very simple, but we're going to use it a lot. Okay. What are some of the applications of polarization? Well, one of the prominent applications is a so-called liquid crystal display, or LCD. Now, we use LCD all the time, right? It's a primary technology used in today's computer monitors, and often we use it for TV monitors as well. How does LCD work? Well, in the case of a liquid crystal, what you have here is you have needle-like molecules, okay, suspended in a fluid medium. And because they're suspended in a fluid medium, they can freely reorient. They can reorient. And you can reorient them, you can control the orientation by using the electric field. Okay, by using the electric field. Now, because of the needle-like shape of the molecule, light passing through this needle-like crystal can only oscillate along the direction of the needle. It does not oscillate perpendicular to it. So imagine if I have a beam of light that's unpolarized, okay, after going through a panel of liquid crystal, half of the intensity will go through, right? Half the intensity will go through. But what I want is to use this liquid crystal panel to form an image of dark points and bright points. How do I do that? Well, the idea is I'm going to divide the liquid crystal into small pixels, okay, small areas. Each area is a pixel, and that pixel really is controlled by a needle-like molecule, and the orientation of this molecule is controlled by an externally applied electric field, which depends on the source. Okay, depends on the source. Suppose I want a dark spot. Okay, suppose I want a dark spot over that pixel. How do I do that? Well, I have behind the entire panel of liquid crystal, I have uniform illumination. Okay, uniform. So light would actually pass through everything if there is no liquid crystal. But in order to block the light so that it becomes a bright spot, dark spot, what I do is I first polarize the light in the back. So light is polarized, say, in this direction. Okay, in this direction. Now, in order to block the light passing through, what I have to do really is I apply an electric field so that in this particular pixel, the LCD molecule is oriented like that. Okay, so light being polarized in this direction cannot go through anymore. Cannot go through the liquid crystal panel in this particular pixel area, so that this becomes a dark area. On the other hand, how do I get a bright spot? Simple. I have to turn this thing back by applying the proper electric field, so that the polarization direction agrees with the light going through. So light will pass through. It becomes a bright spot. Okay. So this is how you produce an alternating black and white image going through liquid crystal. So you have this polarized light first, and then you have to, control the polarization of individual pixels of liquid crystal display using an electric field. That electric field, of course, depends on the source, depends on what kind of picture you want to get. So, intrinsically speaking, the liquid crystal display can give you only a black and white image. In fact, in the early days, liquid crystal display are black and white. Okay, they are black and white. Now, how do you get a color image? Well, actually, to get a color image out of LCD, what you do is use filters, color filters, so that you get red, green, and blue, okay, by filtering out light. So, you just treat different colors using a separate set of LCD, basically. That's what you do. Okay, so each will allow certain kind of light to go through because you filter out other lights. When you add them all together, you get a color image. Okay, so that is one prominent application of polarization.